Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of that day. So we're going to start building towards being able to write aqueous solutions and reactions with the chemistry that matters and try to cut out some of the periphery. But before we do that, we got to build skills. So we're going to start with what's really going on in solution when, say, an ionic compound is in water and it's aqueous. Before we do this, I want to bring up a concept from the latter part of the 19th century. Svante Arrhenius, the brilliant scientist, came up with this idea of ions in solution and conducting. And to simplify it, he basically came up with this idea of an electrolyte, which is any substance that dissolved in water allows for the conductance of electricity. Pretty easy to measure. You can have an open circuit light bulb. You can put it in a solution, see if it glows. If it does, boom, conductor, electrolyte. If it's not, it doesn't. So what is Gatorade talking about when they say essential electrolytes? Well, of course, Gatorade is an energy drink, and you're supposed to drink that when you sweat. And if you ever tasted your sweat, it tastes like marker. No, it's supposed to taste like salt. It tastes like salt. So that's really what they're talking about putting back into you. So the one thing I want you to get out of this entire video we're about to sit through is electrolyte means ions. Ions, electrolyte. Electrolyte, ions, same thing. So we're talking about things with a charge in solution. We're talking about salt. So when they say essential electrolytes, they pour salt in your drink. What you need if you've been sweating. If you're sitting around doing nothing, probably not a great idea. Okay, which is why they made the Gatorade Light and some of these other things as years went on. Okay, so back on topic. Electrolyte, ion. Electrolyte, ion. That's what allows for electricity to pass through. And you're probably sitting in a room right now that has outlets. And no electricity is shooting through the outlets. Why? Because there's no ions in the air. The air is made out of neutral things. There's nothing to help carry that charge across the room. Nothing to help it conduct that electricity. And water is the same way, believe it or not. Except for we never really have pure water. There's self-ionization in there, but there's also, if you're talking about a lake or a river or a pool, it's touching stuff. It's touching rocks and dirt and earth and air. And all of those things bring ions with them. So you certainly wouldn't want to sit in a pool when it got hit with lightning. So it's still good advice. Even though water's an insulator by nature, you still want to get out of a thunderstorm, lightning storm. Okay. So generically, some metal, some non-metal. We take that salt, we throw it in water. Typically it dissolves. Not always, but typically. And it'll become aqueous. This is a lot of the time how we write it. MX, aqueous. It in no way, shape, or form reflects the actual chemistry of that molecule. As soon as that gets in solution, the cation and the anion are going to act independently. They're going to be their own entities, and they really should be represented as the cation plus the anion. And then both of those, if we break up a piece that's aqueous, both the pieces are going to be aqueous. Now, what's this really look like? Well, we have the cation, and then in water, and this is really something we don't get into until the very, very end of the semester, but the oxygen on water has a little bit of a negative charge. A little bit of static electricity, if you will. It's negative. And the hydrogens are positive. So what happens is these cations, these metals, they attract the oxygen end of water around them. And this could be anywhere from 4 to maybe even a cluster of, say, 25 or 30 waters that would drag around with it. Normally, it's probably about 6 to 10. So you get about 6 to 10 water molecules that coat this ion, and they come and they go. And this is a dynamic picture. I don't want you to think this is like a crystal. It's pretty dynamic, but that's what this AQ means. It's an ion coated in water. And it's that coating of water that acts as an insulator and allows it to move through solution and act independently. And it does its own thing. Same thing with the anion. Except now, instead of attracting the oxygen end, the negative attracts the hydrogen end. And again, I tried to draw this pretty haphazard because that's really what would happen in solution. There'd be some order, but not, they're moving, they're vibrating, they're coming and going, new water comes in. But generally speaking, the hydrogens are going to be attracted there, and it forms a little barrier, a little insulation barrier that allows this to move and act independently. And I think that's important to understand what's really happening behind the scenes, because otherwise the rest of this chapter isn't going to make a lot of sense. So this is why we're doing this. This is really the chemical, and this doesn't really exist. So let's start talking about this process a little bit more seriously. In a lot of compounds, this pretty much happens 100%. This is the only form we see are the individual ions. This moves 100% over, and that's something we call strong electrolyte, and that's going to be the topic of this video. Not to give away the next video, but there's a lot of processes where this only happens maybe 1%, 2%, 3%, 0.04%, a very small amount, in which case this is actually the best way to represent the compound. And I'm sure this causes confusion when you're learning chemistry. But these ones that break up all the way, we're going to call strong electrolytes. The ones that don't, we're going to call weak, and I'll save that for the next video. So, strong electrolytes, just to summarize, once again, 100% break up into ions. And again, I want you to think electrolytes equals ions. So, 100% breaks into ions. And how will I know a strong electrolyte when I see one? There's two different strong electrolytes I expect you to recognize. I guess three, really. Your polyatomic, so that's going to anything that starts with ammonium. So again, we always put the cation first. Chemistry is a happy, positive place. So NH4. So if it starts with NH4, we're going to break that up. Strong electrolyte. Starts with a metal, and we're putting it in water. Breaks apart. Strong electrolyte. And then lastly, strong acid. So once again, an acid is something that starts with an H. And then the question, of course, is going to be, well, how do I know it's strong? And this is one of these few cases where I have to say this. Memorize this list. This is the standard list everybody in the country uses for Chem 101. All the textbooks use this as their list of 6. There are more, but this is the 6 we teach you all. Or the 6 most commonly used. Memorize them. Most people already think HCl, hydrochloric acid, dangerous. Good. Strong. The stronger it is, the more dangerous it is, and vice versa. So HCl, strong. The other ones in its family. So just follow down from HCl. Right below Cl on the periodic table is Br. And right below that is what I like to call the friendly acid. Not because it's safe, but, you know. HI, so hydroiodic acid. Nitric acid, you've probably been trained that that's really dangerous. Sulfuric acid, you've probably heard these words, and these are dangerous. And then this one we don't let you use too much because you can form explosives with it. So for very good reason, we don't give it to you in the lab. But perchloric acid is also a common strong acid. So those are the 6. I hate to tell you this, you just got to memorize them. So how do we use this idea in a practical sense? Well, here are 3 different strong electrolytes, and I would like you to break them up to demonstrate what's really going on in solution. So what I always like to say with these problems is, first of all, you need to know it's a strong electrolyte. Metal, non-metal. Strong electrolyte. Metal, non-metal, strong electrolyte. How about this one? Oh, it starts with H, that's an acid. Wait, is that one of the 6 I memorized? Yep, it sure is. I memorized that. I paused this, I memorized those 6, and then went to the rest of the video. I already knew that was strong acid. All right. If it's a strong electrolyte, you're just going to cut off the first thing. And then on the left of the line is your cation, on the right of the line is your anion. And then we just got to think about what these things look like. So Ca by itself. And then this needs to all stay together. Don't annihilate molecules. If you annihilate this into more than 2 pieces, you've done this wrong for my class. SO4. So our choices are, this is either 4 of everything that comes before, or it's part of a polyatomic. The easiest way to do this is 2 capital letters, all stays together. 1 capital letter goes out front. I see 2 capital letters, this all stays together. And then we have to put in the charges. Calcium's in family 2. Sulfate I've correctly memorized has a -2 charge, and I'm done with that problem. It's balanced. We have 1 of each. If we look down here, same idea. H is aqueous. It's in family 1, so it's +1. NO3 minus, again, 2 capital letters. Keep it all together. I've correctly memorized the charge there is -1. It's a 1-to-1 ratio. All of this is balanced as well. Now if we look at this bottom one, here's what I mean by that. So we have a 3 here. It's not a hunk of K3. It's actually 3 individual Ks, so 3 potassium ions. So there's only 1 capital letter there, so we're going to bring it out front. So this becomes 3 potassium ions. And then once again, 2 capital letters, so we're going to keep that whole thing together. So PO3, 3 minus. And that's balanced and we'd be done. So this breaks into 4 ions in total. This is 2 and this is 2. Let me show you one other quick example because I didn't do any like this. But if I were to take something like magnesium nitrate, it should be even easier when it puts in parentheses. Whatever's in parentheses, that stays together. And this number comes out front. So it's become magnesium 2 plus 2NO3 minus. Typically speaking, it's great when they put it in parentheses because they're telling you what the ion is. And then whatever's outside parentheses, that always comes out front. So I know a little bit confusing. One capital letter, bring it out front. 2 capital letters, leave it together. We'll do more of this. We'll certainly practice this. You'll get good with it and comfortable with it. And I look forward to that point. And so should you.